Our next speaker is Matthias Seel. Matthias leads the research group Glass, Glass, and is head of the laboratory Glass Competence Center. His research areas are additive manufacturing, processing strength and structural applications of glass. He's also a member of the standardization committees, and he heads the task group of the bending strength of glass, the European standard, and also the working group edge strength and thermal breakage. Matthias will talk about the novel tempered flat glass and its potential. Matthias, floor is yours.
Thanks, Bert. Thanks for the kind introduction. Today I present to you some novel tempering method for flat glass, but not only for flat glass is this possible to use, and also the potential in the future. We deal with glass here, and we know glass is very strong in compression and it's weak in tension. This is the problem. We know this. We have to recognize this also during design process. Sometimes we had also residual stress inside from the tempering process. These are desired residual stress, and we had also from the cooling process some complicated constructions, also not desired residual stress. And residual stress and the cracks on the surface leads here, you can see here, to cracks. We can avoid this. Okay, then we had not only cracks in such big glass cubes, we had also some cracks in such walk-on glazing. You can see here in a church in Arnhem. And we know that the strength of glass is the quality, more or less, of the surface. There are a lot of cracks in the surface. Here you can see under the microscope. And we know that here on this chart, this is the strength in megapascal. This is the crack depth. This is a function, more or less, here in log scale. And we know the internal strength of glass is in a region over 10,000 megapascal. But if we have cracks which are visible, we are more in a range here of 50. And this is the range, more or less, we deal with architectural glass. Maximum, I would say, 150 for chemical tempered glass. What we can do, we do compression on it. Also, Mr. Cafani said this also. If we had a crack, if I do this is clear, we had crack growth. What we can do compression on it. This was the trick we can do. And we had also some limits from the architectural glass. Here you can see different pieces of glass, different thicknesses, different materials. It's not only soda lime glass. This is the soda lime glass standard in Europe, and for the building sector it's only allowed to use this thickness at the moment. Okay, but we know also from the display industry and so on, and from Corning and also Schott, they can produce really thin glass, up to 30 microns, I would say. Okay, but can we do a pre-stressing of this? For the architectural glass, this is possible that we can do the pre-stressing up to 2 millimeters, more or less. This was not possible. We can do the chemical tempering, yes, but this is expensive. Okay, now I want to talk about the typical methods, how we can pre-stress the glass. I think you know the thermal tempering process or pre-stressing. We do some pre-processing, we cut the glass, we clean the glass, we grind it and so on. Then we bring it in the furnace, heat it up. It depends a little bit on the thickness and is there a coating on the glass surface. We heat it up in a few minutes, then we do a rapid cooling in the quench, and then we save the energy inside the glass, and we had tension in the core and compression at the surface. We had heat up the glass in a range of 630 degrees, more or less. It depends a little bit. Okay, cool industry process. It works very well. But we had also some disadvantages of this process. We had some distortions, roller waves, and so on. We had some problems. There are some discussions yesterday with the distortions, also with the lamination. We had the roller waves, and we had also some anisotropic effects. We don't want this, and the architects don't want this. Okay, I think this is clear. And yes, we had limits. The normal furnace can pre-stress minimum level 3 millimeter. It's also possible to do 1.5 millimeter, but not everyone can do this. Okay. This is in general possible with the thermal tempering process. What do you think? What thickness is this? This is the fracture pattern of a thermal tempered glass, pre-stressed glass. What do you think? Bert? It's really thin. It's 2 millimeter. You can count this if you are right. You get minimum 1 beer from me. There's a lot of energy inside. This was from the theory possible, but not really good. It's too expensive. What we can do, we can bring ions inside. This is the chemical tempering process. It's used more or less for the displays, also for the yacht companies or the windows of the yacht glazing. What we do there is an ion exchange process. We had the glass, we do it in a bath, and what we do, we had the big, really big ions here of potassium, 115 picometer. It's really big, but we had here the small one, the sodium, and this is the exchange process. Ion exchange process is a diffusion process. It works very well. The quality is also very good. We can reach really high values and strengths, up to 600 megapascal for soda lime glass, but it takes time. Minimum, I would say 4 hours up to 2 days. And this is really costly. And here you can see, you can calculate a little bit, the depth of the pre-stress region is not so high. This is also a big disadvantage of the chemical tempering. Here you can see the stress distribution. This is the thickness of the glass. Here you see the compression part, the tensile part. In the stress, this is the typical stress profile for the thermally pre-stressing part. Values more or less up to 100 micron in compression. This is pretty good. It's also possible to go up to 200, but that's it more or less. And we had the big advantage. We had here 20% of the thickness is under compression. This is pretty cool. Chemical tempering, this is the stress profile. It looks totally different. And here's 100 micrometer. This is possible for aluminosilicate glass and a little bit more, but not for soda lime glass. The border is, I would say, 50 microns, sometimes only 10. So, and now the question is, what happens if there's a crack and the crack is larger than the 10 microns? We have to think about this. Okay. And now there's a new method. It's a hybrid approach. It's a thermal and it's a combination between thermal and chemical pre-stressing. What we do, we clean the glass, do the pre-processing, then we heat it up in the range of the normal tempering for the thermal tempering. Then we use, as this in the furnace. Then we had here the salt bath with the potassium inside. It's an ion exchange process also. Then we roll it in this bath, and it takes more or less, we have to heat it up also some minutes, and then we bring it in this bed. It takes more or less 30 minutes and not many hours. And then we have to wash it. And then we had both. We had, because it's a heat shock, this is heats up, bring in the bed, rapid cooling. We can transfer a lot of heat, and so we can do also bring residual stress inside from the chemical, from the thermal part and also the chemical part, and it goes very fast. This was the image before. This was the facility. It was at the moment a batch machinery. It will be hopeful that we can do it also not only in batch, in line. Okay. Now I come to some results. We conduct also some tests. We buy glass, one batch, 100 by 100 millimeter, do the grinding, cutting, grinding, and so on. Then we produce 4 millimeter thickness, also we use the 4 millimeter thickness. We had normal annealed soda lime glass, then we use this for heat strengthened glass, to make heat strengthened glass out of it with a company. Then thermal toughened glass, the fully tempered glass, then chemical strengthened soda lime glass, and then also the novel toughened glass. Here you can see the standards, and we conduct different tests, anisotropic test, residual stress measurements, fracture distribution test, and also the strengths. This is also very important. Okay, let's talk about the results. Here you see we do some scalp measurements. I think you know the device. We can measure with this device over the thickness, the stress profile. It was pretty easy, more or less. This is a typical stress profile for fully tempered glass or thermally toughened glass, and this is the retardation profile you can see below there. These are the typical values. Here we are in range over 100 megapascal or Newton per square millimeter. This was the measurement for the chemical part. You see also the difference, also here in the depth, some microns. I think this is also typical, also the retardation profile. This was the measurement of the stress profile for the hybrid approach, the novel toughened glass. It was at the moment only possible to measure the thermal part. Here we are in the range of 30 megapascal in compression. This is the retardation curve. It was at the moment not really possible to measure with the scalp device also the stress, the introduced stress from the chemical part of the novel process. But I show you some results that it works. Here you can see the mean value in megapascal of the series in the stress measurements. We had 3 samples, 3 different measurements, and these are more or less the typical values. The heat strengthened glass, it's a little bit too much. Here for the chemical strengthened glass part, we are in the range of 200 megapascal, and here for the novel toughened glass, we are in a range of 30. Okay. Let's also take a look on it. We do some anisotropic measurements and fracture distribution tests with our cullet and line scanner. Here you can see the anisotropic effect of normal heat strengthened glass and fully tempered glass. You see dark regions and light regions, and the difference between is more or less the difference in the residual stress distribution. And sometimes you can see this. It's not so cool for the architects. Yeah, okay, this is a typical image. Now let's take a look. Chemical strengthened glass. This is perfect. No anisotropic effects. And now the novel one, it's a mixture between. We had here near the corners also the same like this, but not too much. And we see here in the field region more or less nothing. No anisotropic effects in the field region. This is pretty cool. Let's go to the fracture pattern. These are the typical fracture pattern. These are here 1 centimeter. The fracture pattern for the heat strengthened, it's too much, I know. This is the normal fracture pattern for the chemical strengthened glass, and it's more or less the same also for the novel toughened glass. And this is pretty helpful for the post-package behavior. I don't want to build with this glass, laminated safety glass, as an overhead glass. Okay, fracture pattern as an anisotropic things. We conduct also a double ring bending test. Sorry for the miswriting there, the double. We do a typical double ring bending test with adapted load ring and support ring for this glass, and I want to come to the results. These are the fracture pattern on the left side or on the right side. Left side from you. You see the fracture pattern for normal annealed glass. This is typical. We see also here the fracture pattern for heat strength and fully or thermally toughened glass. It's okay. A lot of energy is inside. If we take a look here to the chemical pre-stressed glass. We see a lot of energy inside here within the load ring. Also we need a lot of energy force to I would say, to destroy the glass, and also for the novel toughened glass. Okay, now I come to the values. We do some statistics, two-parametric variable distribution. These are the expected value, like the mean value. Here we are the typical range of the soda lime glass for this load ring configuration. Here the normal part for the pre-stressing, thermal pre-stress. Here 600, also here we are 250, here 600 more or less for the chemical thing. And for the novel part, for the novel toughened glass, we are also in the region of 600. Very tough. But we had also some issues. We had also one sample with a minimum value of 140, and so we had a little bit the destruction. It was not an outlier at the moment. We had a large variation in coefficient, and so the characteristic strength is not so good. But we work on this. Okay, but a great advantage. We conduct also some ball drop tests here, also with the size of the sample. Here you can see the ball drop is a steel ball. So it's a steel ball on the right side, the noble toughened glass on the left side, the thermally toughened glass on the left side. We can see the break edge over 700 millimeter drop height. This was not so good. On the right side, it was not possible to go higher. Also, we had also impact resistance regarding to this. I want to conclude now. We had with the novel tempered process, we have less anisotropic effects. We had a better quality for the glassing, and also with the roller waves, because the process is totally different. We had also no issues with the roller waves. The measurement of the stress profile is hard. We need new methods for this. We had a rough crack pattern. This is pretty cool for a high load-bearing capacity in the post-breakage behavior state. We had very high strengths, like for the chemical strengthened glass. So we can produce also high-performance glass for fire safety. We can substitute borosilicate glass because the thermal shock resistance is also very high. And the process takes not many hours, only 30 minutes. It's also very fast. And so if it's fast, we can do it also as a cheap process. And it's also possible, we conduct the tests now, that we can do this for thin glass, not only for the minimum 2 millimeter or something like this. And in the future, with this process, we can pre-stress also such complicated samples, not only the flat glass. It's also possible at the moment that they use the pre-stressing method, the group of result for hollow glass units. So we can pre-stress also this type of glass. We have to check in which region, but I would say it's possible to go in the level of 0.5, 0.4 millimeter thickness. And I think this is a great achievement also in the future. Thanks for your time. If you have questions, please ask me.